In this video, we're going to take a look at a couple different kinds of quadrilaterals. We're going to look at kites and we're going to look at trapezoids. And we're going to see some special qualities of each one of those. So let's go ahead and get started. So the first thing we want to do is actually kind of define what a kite is. And so a kite is a quadrilateral with two pairs of sides that are both congruent and adjacent to each other. So a lot of times a kite looks about like this, which is, it looks like kind of the kite that you might fly on a breezy summer day, right? And what we can tell about the reason why this might be a kite is because perhaps this side and this side are congruent, and then this side and this side are congruent. So we can see they have two pairs of sides that are both congruent and then adjacent to each other, which means they kind of are next to each other, or I like to think of it as they connect to each other at one of the corners. So segment AD and segment CD connect there at that corner, and then segment AB and segment BC connect right there at that corner. So that's what a kite kind of looks like. Now what we're going to be taking a look at is we're going to be taking a look at the diagonals of our kite. So I'm going to draw in the two diagonals of my kite. So I have segment AC there, and then I have segment DB there. Now I want to look specifically at segment DB because there's something interesting about that segment. I notice that at one end point I have point B, which is equidistant from A and C. And that would tell me that point B is on the perpendicular bisector of segment AC, right? Because that's something we learned back in the previous chapter, that any point that's equidistant from the end points of a segment would be on the perpendicular bisector of that segment. But then the same thing could be said about point D. It's also equidistant from A and C, so it's got to be on the perpendicular bisector of segment AC. Well, if both of these points are on that perpendicular bisector, if we connect those points together, that would have to be the perpendicular bisector of my segment. So as a result, we can actually say that this diagonal is the perpendicular bisector of the other diagonal. So we could kind of mark up our picture if we wanted to. We could say that we know there's going to be a right angle there. And we could also say that we know that this segment and this segment would be congruent to each other. And that's actually always going to happen with kites, just by the nature of the fact that these two sides are congruent and then these two sides are congruent. That one diagonal will actually always end up being the perpendicular bisector of the other diagonal. It doesn't happen to both of them. They're not both perpendicular bisectors of each other, because we can look at point A and we can realize that point A is not necessarily equidistant from D and B. So it doesn't have to be on the perpendicular bisector of segment DB. But it will always be true for one of the diagonals. It'll be the perpendicular bisector of the other one. And so that is our first theorem that we're going to be learning about in this video. And it's a theorem that just simply says the diagonals of a kite are perpendicular, but we're also going to want to note that one of them will bisect the other one. Or another way to think about it is how we can say, hey, one of these must be the perpendicular bisector of the other, right? So that's our first theorem that we have for this section. And then our other theorems that we're going to be dealing with for this section all deal with trapezoids. And so I just want to take a minute to define what a trapezoid is. It's a quadrilateral that has exactly one pair of parallel sides. And the reason it has exactly in there is because if a quadrilateral has more than one pair of parallel sides, which would mean it would have two pairs of parallel sides, it's no longer considered a trapezoid. It's going to be a different shape that we're going to learn about in a later video, one that you probably could guess what its name is. But if it has exactly one pair of parallel sides, then it's a trapezoid. So for instance, in this picture, if segment RS and segment UT are parallel to each other, then RSTU would be considered a trapezoid. The parts of the trapezoid that you're going to need to know would be the bases of the trapezoid, which are the two parallel sides. So that is a base, and that is a base. Sometimes we call them base 1 and base 2. Those bases will always be different lengths than each other. One will be shorter than the other. And then the other two sides are called the legs of the trapezoid. So this is a leg, and that is a leg. We would also have angles that have special names. For instance, at the end of my longer base here, we have angle U and angle T. And that pair of angles is called a pair of base angles. We have a pair there, but then we also have a pair of base angles up here. So these base angles come in pairs, and each pair has an angle at the end of one of the bases, right? So angle U and angle T is one pair of base angles. Angle R and angle S is another pair of base angles. Now, trapezoids that are isosceles, all right, so sometimes we have trapezoids that we call isosceles trapezoids. They're isosceles if the legs are congruent. So isosceles trapezoids refer to trapezoids where the legs are congruent. Doesn't always have to happen that way. As we can see here, you can kind of just guesstimate that segment RU and segment ST are not necessarily congruent here. But if we had a trapezoid, maybe something that looked about like this, and we knew that this was congruent to that, and this was parallel to that, that would be an example of an isosceles trapezoid. And so that idea takes us to the next theorem that we're going to want to be aware of. And it's a theorem that says that in an isosceles trapezoid, each pair of base angles is congruent. So if we look at this trapezoid, we see that it's isosceles. It's a trapezoid because these two sides are parallel, and it's isosceles because these two legs are congruent. And that would mean that the two pairs of base angles will be congruent. Or in other words, we would be able to say that angle A down here, which they call angle BAD, and angle D, which they're calling angle CDA, those are going to be congruent to each other. And then also angle B, or angle ABC, and angle C, or angle DCB, those angles would be congruent. So these two would be congruent, and these two would be congruent. Each pair of base angles is congruent in an isosceles trapezoid. Now, actually, from that idea on the previous theorem, we can develop this additional theorem that says that the diagonals would have to be congruent. And let me just show you how that last theorem leads us into this one. If I look at I drew the diagonals here of my trapezoid. All right, diagonals go from one corner to a non-adjacent corner, so from B over to D or from A over to C. And when I drew those two diagonals, I created a whole bunch of triangles. But the two triangles I'm going to look at, I'm going to redraw them over here off to the side. I'm going to look at triangle BAD, okay, triangle BAD, and I'm going to look at triangle CDA. So triangle CDA, which would look about like this. Okay, so I've just redrawn triangle BDA right here and triangle CDA right here. Now I want to transfer the markings that I know I would have over here. I know that segment BA is congruent to segment CD. And I know that in this isosceles triangle, this angle here and this angle here are congruent because originally those two angles are my base angles of this isosceles trapezoid. So I know angle BAD right here and angle CDA right here are congruent. But I can also go ahead and mark segment AD and segment AD congruent to each other because it's actually just the same segment in the original picture. So we could say that they're congruent to each other. And that would mean that these two triangles are congruent by side, angle, side, and side, angle, side. And now once we say that these triangles are congruent, it would mean that segment BD and segment AC are congruent because once we can say the triangles are congruent by side, angle, side, we can actually then say that all of their parts are congruent using an idea called CPCTC. Let me write that out. CPCTC, which stands for the corresponding parts of congruent triangles will be congruent. So once we know these triangles are congruent, we could say that these other parts right here that correspond to each other, they have to be congruent, which happen to be the diagonals of our original trapezoid. So that's kind of the proof of why our diagonals will always be congruent in an isosceles trapezoid. Now the last theorem we're going to look at for this video involves something called a midsegment of a trapezoid. And a midsegment is a segment that joins the midpoints of the two legs, right? So let me just kind of highlight that idea here real quick. The segment containing the midpoints of the two legs, the name of that thing is the midsegment. So if I look down here in my picture, I can see that X is the midpoint of this leg of my trapezoid, and Y is the midpoint of the other leg of the trapezoid. Segment XY is joining those two midpoints, so that is called the midsegment of, that guy there is called the midsegment of trapezoid ABCD. Now, what's interesting about the midsegment is, first of all, it will always be parallel to the bases of the trapezoid. So we could actually add on this little symbol here showing that all three of these segments are parallel to each other. And its length is half the sum of the lengths of the bases. So the length of XY is the length of BC added to the length of AD and then divided by 2 or multiplied by 1/2. It's half of the two base lengths added together. And that's called the midsegment theorem, the trapezoid midsegment theorem.